Okay, let's get started. Today we'll talk about a very challenging but important chapter, probability theory. It's challenging because probability cannot be visualized. Probability represents the prediction about the chances, right? We cannot see chances. So that's why this chapter needs everyone to use your logical and critical thinking skills to comprehend. But this chapter is also important because we are studying business analytics. Basically speaking, business analytics is applied statistics. As you can see, we implement statistical models in computer systems. So if you want to be proficient and a professional in business analytics, you must understand probability theory. Because statistics is about prediction, estimation, right? Last time I talked about what statistic is. We are interested in population, but we cannot survey or study the entire population. That's why we use samples. We predict whether or not the population will follow the sample behaviors. At this moment, we estimate the population behavior by using samples. Every time when I talk about estimation, you must consider probability. So that's why I want to introduce this chapter specifically during this lecture. Let's talk about it. First, let's learn some terminologies about probability theory. We all know that probability can only be any value between 0 and 1. Right? If you see the probability is 0, that means that event will never happen. If you see the probability is 1, then that means the event will definitely happen, for sure, right? Probability can be any value between 0 and 1. I just talked about a term called event. So let's talk about them. First, you want to know what an experiment is. An experiment is defined as an activity that can generate different outcomes. That's called an experiment, right? If you consider all possible outcomes from an experiment, then all possible outcomes consist of a sample space. Sample space refers to all possible outcomes from an experiment. Remember that, right? If you only care about certain outcomes, then certain outcomes are called events. Events. For example, you toss a die. What is the sample space? 6 possible outcomes. 1 dot on the top, 2 dots on the top, 3 dot, 4 dot, 5 dot, 6 dot on the top. That consists of the sample space after you toss a die, which dot you will see. That's a sample space. Of course, tossing a die is an experiment, right? If you want to know the probability of you see 2 dots on the top after you tossing the die, then 2 dots, this specific outcome, is consist of this event, particular event. So tossing a die, which dot you can see on top, will have 6 possible outcomes. You can calculate any dots on top after you toss a die. Now you know experiment, now you know sample space. You also know an event. An event is just a part of the sample space. Remember all of this, right? For example, if you want to see the sample space of getting a grade from a class, what this sample space consists of? You can get an A, you can get a B, C, D, F. This consists of the sample space of getting a grade, letter grade. If you register an internship class, the sample space of the result of an internship class include only two possible outcomes, pass or fail. Yes, right. Next, you need to know what is exhaustive events and mutually exclusive events. Exhaustive events means that if the event covers all possible outcomes of a sample space, then this event is called an exhaustive event. Mutually exclusive means in each event, you can only get one possible outcome, and the different outcomes do not overlap with each other. So we just said in the letter grade example, if you count all possible letter grades in a class, then these are called exhaustive events. For example, in our class, some students get A, some students get B, C, D, and F. If we have all possible grades in this class, then this class consists of an exhaustive event because we covered all possible letter grade. Let's say in another class, some students get A, some students get B, some students get C. That's it. Can we say that class is an exhaustive event? No, because not all letter grades are covered in another class. This is what exhaustive event means. In exhaustive events, each event must cover all possible outcomes in a sample space. Mutually exclusive, simply speaking, can be understood as either or. You can only get one possible event in one experiment, in one event. You cannot get two possible outcomes. For example, in the internship class, we only have pass or fail. So each student can only get one grade, either pass or failure. Yes. If you can only get one possible outcome, not two or more, then that event is called mutually exclusive. Very easy to understand, right? This is what mutually exclusive events means. We just talk about the example of the letter grade and pass or fail in different classes, right? Sometimes we will use visualization to visualize two events. We call that visualization tool a Venn diagram. Venn diagram. For example, in this case, we have a yellow square, right? We use yellow square to represent all possible outcomes from an experiment. That's why you see a letter S. That means we want to use this yellow square to visualize, to represent a sample space. Yes. Sometimes we only care about two events, right? The two events could cover common area. So that's why you see two bubbles in the middle, right? We could use this kind of chart. This is called a Venn diagram to visualize sample space and events. If you want to calculate the common area the common area between event A and event B, we call A intersection B. When you write it down, you will write a letter N and B. It looks like an N, right? But it's not N. It's actually an arc. That means you want to focus on the common area, so overlap the area between A and B. Right? You see, A intersection B. The symbol in the middle is an arc, right? It's an arc. That's a common area between A and B. So if you want to visualize it, we have an orange bubble to represent event A, blue bubble represents event B, and then the common area is shown as purple color. Can you see that? Right? A intersection B is represented by the purple area in the chart. It's important to understand this diagram because later when we talk about the base theorem, I want to use this chart again. Sometimes you want to calculate the probability of A or B, then you basically want to calculate the two bubble areas, right? The probability. In that case, we use A upside down arc B. We call this A union B, exactly. A union B. If you only want to calculate the overlapped area, we use A intersection B. Very good. We also want to calculate, sometimes we want to calculate except event A, what is the probability? We call the exception complement of event A. We use AC to represent complements of event A. By the way, do not write I in the middle. I see lots of reports before. Complements of event A. If I in the middle, that means free. Complements breakfast if you book a hotel room, right? But complements, if you add an E in the middle, that means the other part of something. Complement. Complement means supplement, right? Except for event A, what is the event? So we use AC to represent complement of event A. Remember that. Remember that. So obviously, if you want to visualize the complement of event A, that will be the yellow area, right? Why? Because complement means we do not consider event A. Event A is already in the orange bubble, right? Complement will be the yellow area. Except for event A, what is the probability for complement of event A? Any question about this? Now we need to know some features, characteristics of a probability. We already talked about the probability can only be any value between 0 and 1. It can never exceed 0 or 1, right? It cannot be below 0. It can never be exceeding 1. Yes. It can only be any value between 0 and 1, including 0 and 1. If you have a mutually exclusive events, the total of all mutually exclusive events equals to 1 exactly. Yeah. because each mutually exclusive event can only represent part of total probability, which is 1. We have several ways to calculate a probability. 3 ways: subjective, empirical, and classical. Subjective probability calculation means your estimation, your personal opinion. According to my experience in the IT industry, what could be the probability of Apple laying off employees in the next quarter? That is your personal estimation. We call this subjective calculation, right? Empirical. Empirical means you look at the historical data, and then you use historical data to calculate probability. For example, among 10 years, 3 years Apple laying off employees. So what is the probability for Apple to lay off employee? 3/10. Then the third method is the focus of this class, classical calculation. We use logical relationship between data to calculate the probability. This is the most rigorous, most challenging calculation. So we will learn certain equations and formulas to calculate classical probability. This is why I said this chapter is challenging because, as you can see, the keyword here is logical analysis. It depends on your logical thinking. Yeah. Okay, let's see some calculation. Obviously, if you want to calculate the probability of A complement, you use 1 minus the probability of event A. Any question about this? No? The probability of sample space equals to 1, because sample space represents all possible outcomes, right? Let's see this example. "37% of female who attends the open house event will purchase a membership. What is the probability that a randomly selected female will not purchase a membership?" Will not. That will be the complement of will purchase a membership, right? So we already know 37% of female will purchase a membership. Then when we calculate will not purchase, 1 minus will purchase probability, 1 minus 0.73. So the probability of female who will not purchase membership equals to 1 minus 0.37 equals to 0.63. Yes. Now let's take a look at the addition rule. We just talked about how to use a Venn diagram to visualize two events relationship, right? If you want to calculate the probability of A union B, how do you calculate it? Obviously, probability of event A plus probability of event B minus probability of A the intersection B. Why minus? Because we counted the overlap parts twice, right? It overlapped when we calculate the total of PA and PB. That's why when we calculate the probability of A union B, we must subtract PA intersection B from the total of PA plus PB. Exactly. I have a question for everyone. What if the two events are mutually exclusive? How do we calculate A union B? How do we calculate that probability?
A plus
Mutually exclusive.
So that will be probability of A plus probability of B.
And then nothing else, right? Why we don't subtract P A union intersection B anymore? Because they are mutually exclusive, meaning that they are not overlapped. Yes. Right? They are not overlapped if they are mutually exclusive. P A intersection B equals to 0. Yes. Remember, this is called addition rule. PA union B equals to PA plus PB minus PA intersection B. This is the general format of addition rule. We have a special format, which is when A and B are mutually exclusive, when we apply the addition rule, PA union B equals to PA plus PB. That's it. Let's do some exercise. What is the probability that he gets an A in at least one of the course? What do you think? Of course, you can see the answer, right? But I want to challenge you a little bit. By the way, every time when you are given a probability question, you always write down the events first. Always write down the events. You can use event A to represent something, event B to represent something else. That's fine. You can also use like event S to represent the events, event E to represent the second event. Doesn't matter. But no matter what, you want to write down the events first. Let's use AB, right? Let's use event A represents the student gets a in statistics class. Event B to represent the student gets a in economics class. What are we trying to do here for question A? We want to calculate the probability of A union or intersection. Union B because we said R, right? We didn't say he got A in both questions, both subjects, both classes. We said we want to calculate he got at least A. So either or, right? Or both, doesn't matter. That's why I want to calculate probability of A and A union B. In this case, the textbook uses AS to represent the event of getting an A in statistics, right? AM to represent the event of getting an A in economics. Doesn't matter. You can change AS to A, AM to B. Doesn't matter. It's just some symbols, right? But you do want to write down different events. So we want to calculate a probability of a union, right? According to what rule? Addition rule. The probability of the union equals to PAS plus PAM minus the overlapped area. Why we need to subtract the overlap? Because getting A grades in both classes are not mutually exclusive. right? So as long as we are given the probability of getting an A in some statistics, the probability of getting an A in economics, and the overlap probability, we can calculate the probability of the union event, right? Do we have all of this information? Yes, we do. PA, PAS equals to 0.75. PM equals to 0.55. Overlapped probability 0.4. So 0.75 plus 0.55 minus 0.4. That's it. Let's take a look at the second question. What is the probability that he does not get an A in either of the classes? He does not get an A in either. That means this event is a complement of he got an A, at least an A in one of the class. Yeah. So as long as you calculate the probability of the union, then you can calculate the complement of the union event. That will be 1 minus the probability of the union. Right? Are we all good? I don't want to lose anyone in this maze. This is like a maze game. You will see more and more challenging questions, right? Okay, before we move on, I want to emphasize that this is how you look at, the mutual exclusivity of two events, right? If two events are mutually exclusive, we say P A intersection B equals to 0. Later, we'll talk about another important concept called independence. Independence. Remember, when you evaluate if two events are independent, you use different calculation. PA intersection B equals to 0 only applies if you want to evaluate whether two events are mutually exclusive. This is not applicable when you evaluate whether two events are independent. Remember what I said, right? So later when we calculate whether two events are independent, we'll use different calculation. Okay. Next, we want to talk about conditional probability. If you just calculate PA or PB, you don't consider the relationship between two events, right? You look at each event as an independent event. You assume that there's no dependence between the two events. If you only calculate PA, if you only calculate PB independently, we call this unconditional probability. However, in business world, some factors are dependent on the other factor. So we have to consider conditional probability. This is how you calculate conditional probability. You see A pipe B, right? A pipe B. This reads as given event B happens, what is the probability of event A? Are we all good? Given event B has happened, what is the probability of event A? This is called a conditional probability, meaning that the probability of event A dependent on event B. How do we calculate it? This equation shows you. Right? Probability of A intersection B divided by probability of event B. This is very, this makes sense, right? Because we said we want to calculate the probability of event A, even that event B has happened. That's why we want to use the probability of intersection divided by probability of B. We said we assume that event B has happened. What is the probability of event A? Right? If you assume that event A has happened, you want to calculate the probability of B, you can do the same, similar. If you assume probability of A has happened, then the denominator should be PA. Numerator still PA intersection B. So it depends on which event you assume has happened first. Okay, let's see an example. This example is closely related to everybody here, right? I appreciate the textbook gives you this example. So let's assume that event A represents finding a job. A business college student finding a job. We know that the probability of that event is 0.8. And then we want to calculate some conditional probability. The condition is, given the student has previous work experience, the probability of the student getting a job increased. Increased to how much? 0.9, 90%, right? You see, events are not always independent. Some events are dependent on other conditions, right? This also tells everyone that if you want to increase the chance for you to be employed, what do you need to do? You need to have a previous work experience. Yeah, that's why it's very important for everyone to get an internship ASAP. Don't you agree? Right? I happen to do a very interesting research. I want to share with everyone. That's why I agree with the textbook information. Do you know Dow Jones? Dow Jones is a stock index. So this company is a stock investment consulting company. It's called Dow Jones, right? This company selected the most influential 30 companies in the US and then summarize them as an index, a stock index. So this stock index will show you how a stock market performs in one day, every day. Right? I was curious the background of the founders of the 30 companies. The founders, I'm not interested in CEOs because CEOs are professional managers, right? They are hired as a manager. I'm interested in the founders. Do you know what I found? What is interesting is almost 40% of the founders never went to college. That's interesting, right? 40%. They never went to college. What does this mean? That means if they don't go to college, they hire people. If they go to college, they will be hired. They will work for other people. Of course, this is a joke, right? But you know what? The most important lesson I learned from their background is doing is very important to a business person. Doing. Learning, of course, you learn models, you learn business knowledge. Learning is important, right? But the doing is equally, if not more important than just the learning. I'm not, I'm not asking you to drop out today. I'm not saying that. I'm saying I feel that the current education model focuses on learning, but you are in business school. You are not in engineering school. If you are in engineering, you can lock yourself in your apartment, read all kinds of literature, textbook by yourself, because this is what they do. We are in business school. As I said in the first class, you deal with people. How can you learn people skill if you don't do? Think about it. That's why I agree with the textbook. If you have a previous work experience, that will increase the chance for you to find a new job. Exactly. So I highly recommend everyone, no matter you are international student or US student, I highly recommend everyone find an internship ASAP. This is what I learned from this conditional probability. When I read this example, I immediately think about my previous research about Dow Jones founders. Which company is in Dow Jones? Apple. Did Steve Jobs go to college? No. Amazon is also part of Dow Jones Index. Did Jeff Bezos go to college? No. No. So that means in business world, doing is very important. Doing. There is an interesting thing. When people teach you, it requires lots of people. When things teach you, just one thing will make you understand. Okay. We just talked about the difference between conditional and unconditional probabilities, right? Unconditional means you just calculate the probability of the event directly. Conditional means when you calculate the probability of the event, you assume that another related events have happened. So whatever letter you use after the pipe, that means that event has happened after the pipe sign, right? In this case, we assume that event B has happened. Why? Because event B is written after the pipe sign. A pipe B. That means we assume that B has happened. We want to calculate the probability of right? This is a conditional probability. Let's do an exercise. What should you do first? Write down the events exactly, separately, right? Not always together. So what is event A? No, when you write down the events, you don't consider the chance or probability. You simply write down the fact. Yeah. So event A is country A, no, not 60, don't mention probability as I said. You simply write down the fact. The fact is event A is country A does poorly. That's it. Because event is about the fact, right? If I talk about the probability of event country A does poorly, then you mention 60%. Event A is simply the fact country A is doing poorly economically. What is event B? Country B is doing poorly economically. Right? What are we doing? What are we trying to do? Given what is the probability of country A does poorly given country B does poorly? So when you write down as the probability symbol, you write down you want to calculate P A pipe sign B. Exactly. How can you calculate P A pipe sign B? Equals to what? Equals to this. Don't forget. Right? This is the equation to calculate probability, conditional probability. Do we get all the information? Yes, we do. Do we have P A intersection B? It's given. It's a given. Let's talk about here. There is also a 16% chance that both countries are doing poorly. So P A intersection B equals to what? 16%. Do we need to calculate the PB? Is PB given? Right? According to the equation, PB is given too, right? PB equals to what? 25% is given. So what is the probability of PA given B? 16% divided by 25%. Who does not understand this? Please raise your hand. All good, right? All good. Let's do another example. Exercise. Practice make perfect. So as long as you keep practicing, even if a concept is challenging, you will understand. Any answer from the class? What do you do first? Write down the events. What are the events we are talking about here? Event A, event A, a new customer becoming the next customer paid member. That's event A. Event B, a consumer reacting positively to a social media campaign. right? Do you all agree or not? So what are we trying to do? We try to calculate the probability of event A, the probability for next person who knows your social media campaign will become your paid customer. Yes, that's probability of event A, right? And event B, the probability for a customer to react positively to the social media campaign is given. How much? 14%, exactly. Do we know, given the customer reacts positively to the social media campaign, the probability for him to become a member, a customer? Do we know? Yes. Yes. What is, how much? 24%. Yeah. All of this information are given already, right? So can we calculate the probability for the person who know your social media campaign to become your customer? Yes. Right? Here I use different letters to represent different events. Right? Doesn't matter as long as you differentiate which one is the conditional event, which one happens first, which one you want to calculate, you can use different letters. This is a variation of the conditional calculation, right? We just move the numerator part to the left side of the sign. Yeah. It doesn't change any mathematical relationship. We just move different parts to the left side. So the probability for a customer for a person to become your customer is 0.0336. 3.36%. Have we got all good? Did I lose anybody in this class? Not yet? Okay, that's good. Okay. Let's see another example. Let's say I want to use two events to represent these two events, right? I want to see event A is my desktop crashed. Event B is my laptop crashed, right? Also, I'm given that there is a 0.12% chance that both computers will crash, meaning that given my laptop crashed, the probability that my desktop also crashed equals to what? 0.12%, right? 0.12%. So I'm able to calculate according to this event, according to the conditional probability calculation. I know that PA intersection B is what? 0.12, right? What about the PA? 0.02, 0.02, right? What about the PB?
0.06.
0.06. So as you can see here, PAB in this case exactly equals to PA multiply PB, right? PAB equals to PA and PB. That is interesting. If you have a relationship like this one, we call these two events independent. Remember, I mentioned this term just now, right? Independence. If you want to measure whether two events are independent, PA intersection B equals to PA multiplied by PP. Yes, yes. If you want to measure whether two events are mutually exclusive, PA intersection B equals to what? Mutually exclusive. Exactly. PA intersection B equals to 0. That means two events are mutually exclusive. If PA intersection B equals to PA and multiply PB, the two events are independent. Yes. Remember how we measure the two concepts differently, right? Very good. Which also means that if two events are independent, PA given B equals to what? PA, right? Because they are independent. Right? PA, simply PA. It's easy to understand because if two events are independent, no matter what B happened or not, PA given B still equals to PA. Are we all good? The two equations are equivalent. They are in different format, but telling you the same thing. If two events are independent, PA given B equals directly to PA. It means B is not influencing A. In other words, PA intersection B equals to PA multiply PB. That's it. This is how you measure whether two events are independent. But if you talk about mutually exclusive, PA intersection B equals to 0. Two different concepts. Very good. Okay, now is the most challenging part. We have been talking about how to calculate PA. Suppose we know that event B has happened. Have you wondered one question? Because as business analyst, you, as Steve Jobs said, keep foolish, keep hungry, right? Once you study one concept, you always wonder another question. We just learned, even we know that event B has happened, we need to calculate PA. How do we calculate it? This is the way we calculate it. This is the equation we calculate. Given B has happened, how we calculate PA, right? I wondered one question. What if, given that we know event A has happened, we want to calculate the probability of B? We must use different calculation, right? But is the current equation somehow related to how to calculate PB? Suppose we know event A is happening. There must be some relationship, right? Here we suppose that we already know event B has happened. Then we calculate PA. But what if we know event A has happened? How do we calculate the probability of B? There must be some relationship between the two calculations, right? How can we connect them? This is how. As I said just now, Venn diagram is very important when we calculate conditional probability. Can we use the current Venn diagram, as you can see on this slide, to visualize the relationship between A, B, and the complement of B? Can we? Tell me, do you understand this diagram? Why not? I'm curious. Which one you don't understand?
Yes, right. If the probability of B, if we know that B has happened already, that how do we define that, or how do we connect it together? So I'm trying to figure out how we're going to work.
Right. Let's not talk about that part. Let's look at this diagram first. And then we want to find the connection. So when I calculate the unconditional probability of event A, can I stretch event A into this equation? Can I? Yes, right? Why? Because A can be split into two parts. One part is overlapped with B, another part overlapped with what? The complement of event B. Right? Because no matter what, if you combine them together, you are calculate probability of event A anyway. I want to give you some time to soak it in. If I want to calculate the unconditional probability of event A, I'm going to stretch event A into A intersection B, and another part will be A intersection the complement of B. Because when I combine A intersection B, A intersection complement of B, what is the final result? Even A. You agree? You understand? Yes, right? Very good. Yeah. Who does not understand? Please raise your hand. I want to stretch A a little bit. I'm not only limited to event A. I want to stretch it into A, B, and the complement of B, so that I'm able to stretch the calculation a little bit. As I said, we are trying to find the connection between given B calculate A and given A calculate B. That's why I want to stretch this single event into A, B, complement of B, so that I can make the connection. Do you all agree? All good? So if I can stretch PA a little bit, suppose I already know A. I want to calculate PB. Then what should we write? PA intersection B divided by what? PA. PA. As I just said in the Venn diagram, I stretch the PA into A, B, and B complement, right? So I can stretch the denominator of PA into PA intersection B and the PA intersection B complement. Can I do that? Yes. Yes. So how can I stretch PA intersection B a little bit more? I use PA intersection B equals to what? Equals to this part. PA given B multiply PB. Can I do that? Yes, according to the previous slide, I was doing this. Given I know B, I want to calculate PA, right? Right. Can I stretch PA intersection B complement a little bit? Can I stretch this part? Yes. What is it? Yeah, PA given B complement multiply PB complement. Right. Did we make the connection? Yes, we did, right? Yes. So we are trying to calculate given A, we want to calculate the probability of B, right? But we want to connect this connection with previous calculation. Given B, what is the probability of A? Right? Did we make the connection? Yes, we did. And this transformation is called a Bayes theorem. Bayes theorem.
Is to
Bayes theorem. Very important concept. Since you assume that two events are dependent, that's why we want to calculate conditional probability. And the calculations are related to. We can calculate the probability of event A, given that we know B. We can also calculate event B, given we know A. Yes. Yeah. They are connected. This transformation is called the Bayes theorem. How do we use it? I'm so happy everybody understands the transformation first. Now let's see how we can use Bayes theorem in practice. Very interesting question at the beginning. It looks clueless, right? So many things like telling a truth, the probability of telling a lie, right? What is the reliability? Looks very complex. But follow what I taught you. First, write down the event. when I said write down the event, do not think about the probability yet. Just write down the fact, the behavior, the action. That's it. Because if you consider probability when you write down the event, you basically trap yourself into a hole. The more you write down, the more complex the question becomes. Just write down the fact. What are the two events we are talking about here? Telling a truth. That's one event. What is another event?
Test detecting a lie.
Detect a lie. Yes, yes, right. So I'm going to do this. I'm using event T to represent telling a truth. Telling a truth. Event D as a dog, to represent the event of detecting a lie. Right? So can everyone tell me what is PT? 99%. What is PT complement? 1%. 1 minus 99%, right? I said PT is 99%. So PTC is 1 minus 99%, which is 1%. Right? Okay, this is the first information tells us. Assume that 99% of individuals who go to this test will tell the truth. This is assumed. So if we set T, event T represents telling the truth, PT equals to 0.99, PTC equals to 0.01. Yes. How can we interpret the second statement?
That's the lie. 95%.
It's 95%.
So reliability is considered as 95%. In other words, there is a 95% chance that the test will detect a lie even an individual actually lies. Right? How can we write this into probability format? P, then,
For detection.
and
I.
then.
And then both
That's it, or okay. PD, that's it? No, right? Given, I focus on the keyword given. Given. PD, given pipeline, TC. TC equals to what? 0.95. Right? PD, pipeline, TC. What about the third statement?
5%.
The third statement. How can we present it into a probability format? There is a 0.5% chance that the test mistakenly detect a lie given the person tell the truth. So P what? PD percent given T equals to 0.5%. Yes. Yes. What are we trying to calculate? What is the probability that? Okay, so an individual has just taken the test, and the test detects a lie. What is the probability that this individual is actually telling the truth? Oh, tell me the probability format. P what?
Right.
No, just.
P what? P D or PT? D or T? I hear T, I hear D, I hear E. What about E? Who said E?
No. P.
PT, right? PT. And then what?
Given
D. Exactly. Because this question already asked you. This is a question statement, but it also tells you some information. I already detect a line. So I want to see what is the probability for this person to tell the truth. So I actually want to calculate T as Texas, given D as a dog. PT given D. So how can we calculate? According to the Bayes theorem, can we calculate that? Yes. Yes. I highly recommend everyone to take a look at this slide at home. This is the equation to calculate that. I want to calculate PT given D as a dog, right? According to the Bayes theorem, I can stretch PD a little bit into this denominator, right? The numerator equals to this part. This is all about the Bayes theorem, right? If this equation looks complex to you at this moment, it's understandable because you just start learning Bayes theorem. But at home, you can match the numerator and denominator part to Bayes theorem. You will see how we met it. Yes, this question looks very complex, but actually you only need to figure out 4 probability. The 4 probability will be PT, T as Texas, and PTC. Do we know all of this information? Yes, PT equals to 0.99, PTC 1 minus 0.99 equals to 1%, right? The other 2 probabilities you want to figure out is P, D, given T. Do we know this information? Is a reliability statement, right? The reliability is 95%. We also need to know PD given TC. Do we know that? The mistaken rate, 5%, 0.5%, right? We know all of these 4 probabilities. We are able to use Bayes theorem. Are we all good? Very important factor. So after you plug in all of this number, you find out if the detector detects a lie, the probability for this person who actually tells the truth is what? It's only 34%. What is your assumption before the test? 99%. Do you remember this question statement? Assume that you assume that 99% of the individual will tell the truth. But after the test, what is the real probability? 34%. We call your assumption 99% prior probability. Prior to what? Prior to an experiment, a study. Prior probability. We call 34% posterior probability. Posterior to what? the study, your analysis, your experiment. So you have your assumption, right? But you have to analyze, you have to collect data to test your hypothesis. That's why in base theorem, they talk about two probabilities, prior probability and posterior probability. You use evidence, you use analysis to validate your prior probability. You will find the posterior probability. Are we all good? Okay. If all good, we can move on to probability distribution. When we talk about data, data can be classified into two groups, discrete data and continuous data. Discrete data means they are countable, like integers, 1, 2, 3, 0, -1, and so on. They are countable. Continuous data means they are continuous, they are real numbers. Between 1 and 2, you have 1.2, 1.19999, right? You cannot differentiate between 1 and 2. They are continuous. So for these two types of data, we have different probability distribution. Let's talk about them. Discrete data. We have two important discrete data distribution. First one is binomial distribution. Before we talk about distribution, let's talk about the characteristics of discrete data probability. No matter they are countable or continuous, the total probability of all possible events are still 1, the total, right? Each discrete data probability is just between 0 and 1. And the total of all possible discrete data equals to 1, right? When you talk about the discrete data, you also differentiate discrete data into cumulative data or just the one data. For example, sometimes you want to calculate, let's say in the social media advertisement campaign example, you ask 10 customers, right? You give this social media advertisement to 10 customers. You want to find out exactly 2 of them will become paid member, right? But in another case, you want to find out at least 2 customers. At least 2 customers will become the paid member. Then you have to consider exactly 2 customers, exactly 3 customers, exactly 4 customers, and so on to become paid member. So when you talk about the discrete data, when you calculate the probability of discrete data, you will calculate the probability of getting a specific number and the cumulative probability, the probability of getting a range of numbers, 2 different calculations. When you talk about the continuous data, you only look at cumulative probabilities, the probability of getting a range of data. This is the difference between discrete data and the continuous data. Why we have this difference? Because we just said continuous data is not countable. They are continuous. That's why we always calculate the probability of getting a range of data set. But because discrete data is countable, that's why we have to calculate either the probability of getting one number or getting a range of numbers. Last time I also talked about the summary of a data set. We talked about mean and standard deviation, right? How can we calculate the mean value? We add all these data sets together divided by the sample size. But from the probability perspective, when we calculate the mean value, we will be using each value to multiply the probability of getting that value. That's why you see this equation. You see mu equals to sigma xi multiply p. Xi means each value, each data value. P represents the probability of that particular value. This is how you calculate the mean value from a probability perspective. And we also call the mean expected value. Expected value. We use letter uppercase EX to represent the expected value of a discrete data set. As I said, EX equals to sigma xi multiply p. Also, we have a standard deviation, right? That shows the dispersion of the data set. We will be using this equation to calculate standard deviation. This equation. The sum of the square root of the difference between each value and its mean. That will be the variance of the data set. If you calculate the square root of the variance, you get the standard deviation of the data set. So first you need to calculate the mean according to the probability perspective. Then you want to use each value minus the mean. You calculate the square value of the difference, add them up, that will be the variance. Once you calculate the square root of the variance, you got the standard deviation of the data set. Are we all good? Let's see an example. So we have a manager. He estimated the probability that each employee will perform excellent, good, normal, and poorly. Right? The probability is shown here. Zero 0.15, 0.25, 0.4, and 0.2. And then according to each employee's performance, he wants to give each employee different reward. So what is the expected value of the reward? How do we do that? According to what we just said, we use each reward multiply the probability of getting that reward. That will be the expected value. What about the variance? After we get the expected value, we use each reward to multiply the expected value, right? And then get the square value of the difference. That will be the variance. And then we get the square root of the variance. That will be the standard deviation of the reward. You can take a look at how to calculate these two factors at home. I will not repeat. It's very intuitive. There's nothing to talk about, right? You just follow the equations to calculate the expected value and the standard deviation. Next, let's talk about the binomial distribution. Binomial distribution is used if you find that each event has only two possible outcomes, success and failure. And you will be given the probability of a success. How can you calculate the probability of failure? 1 minus success rate. That will be the failure rate, right? And then you keep doing this experiment over and over again. You will have multiple different results. In some cases, you have failure. In other cases, you have success. In this case, if you want to calculate the total success rate, you use binomial distribution. This is a mathematical calculation, but you are not required to remember this. You can use Excel. I'm going to show you how to calculate by using the Excel function. And also remember that if you have a binomial event, the expected value of a binomial experiment equals to NP. N represents the number of experiments you did. P represents the success rate of each event. If you want to calculate the variance of a binomial event, this variance equals to NP multiply 1 minus P. We just said 1 minus P is what? Failure rate. P is success rate. Let's see an example. So in the US, according to a study, 68% of all US adults are Facebook users. So to each person, what is the probability for this person to be a Facebook user? 0.68, right? What is the probability for this user, for this person to not be a Facebook user? 1 minus 0.68 equals to 0.32. So 0.68 is the success rate for a person to be a Facebook user. 0.32 is the failure rate for a person to be a Facebook user. Now, we want to survey 70 Americans. We want to see among the 70 Americans, what is the probability for we want to survey 100 Americans. We want to see what is the probability for 70 Americans out of this sample to be Facebook users. We use binomial distribution. Why? Because to each person, he can only be either Facebook user or non-Facebook user. It consists of a binomial experiment event. We repeated this event 100 times. We want to see what is the probability that 70 out of 100 Americans are Facebook users. So we use binomial distribution. And we use Excel. We don't need to calculate by hand. I showed this calculation equation just for some interested classmates. If you want to know how to calculate by hand, you can always come back to this slide to find the equation. But in this class, we only use this equation. Binom dot dist. I'm going to type equal to binom dot dist. Here we need to specify four parameters. First is the success number. We want to see among 100, how many what is the probability that 70 out of 100? So the success number is 70, comma. Second is the trial number. That means the total sample size. We surveyed 100, right? And then the third one is the success rate. 0.68 is for each customer to be Facebook user. Here, the last parameter is true or false, right? We want to see the probability of getting exactly 70 customers, 70 Facebook users, exactly 70. It's not cumulative, it's exactly. So we use false. What is the probability? 8%. 0.079%, which means 7.9%. Right? What if I change the question a little bit? I want to see the probability of no more than 70 Americans are Facebook users out of this 100 sample. So I need to calculate the probability of getting 70 Facebook users, the probability of getting 69 Facebook users, 68, 67, down to 0, right? And then I want to add up all of these possible probabilities. But in Excel, we can change just one parameter. Here, when I calculate the probability of getting exactly 70, I use false, right? No more than 70, I change false to true. So I'm able to calculate the probability of each independent event, right? Obviously, that's much larger than just getting one exact number. Remember how to use binom.dist. This is the binomial distribution. Next, I want to talk about the Poisson distribution. This is not a Poisson distribution, by the way. Poisson. Poisson is the last name of a great French mathematician, Poisson. This is how you calculate mathematically, but in this class, we will also use Excel function. I'm not asking you to use mathematical equation to calculate. But remember, the expected value of a Poisson event is mu, the expected value of the data set. The variance of a Poisson event is also mu, the expected value of the data set. So how can we calculate Poisson distribution? We use Poisson.dist, right? Poisson.dist. We just said that if each experiment only generates two possible outcomes, we use binomial distribution, right? So when should we use Poisson distribution? Poisson distribution assumes that your success is proportional to a time interval. Let's see an example. So the sales volume of craft beer continues to grow in the US. According to one estimate, 10.5 craft breweries open every day. Right? So if we have 2 days, how many new factories will open? 10.5 multiplied by 2. If we want to calculate how many factories will open in 10 days, how can we calculate? 10.5 multiplied 10. So you see, the change is proportional to a time interval. The longer, the more. right? In this case, we'll be using Poisson distribution. In binomial, we look at the two possible outcomes. Here, when we use Poisson distribution, we assume that the average will be proportional to a time interval. Of course, you don't need to calculate because we can use Poisson dot dist. I will show you. So in this case, I'm going to select a new cell. And then I'm going to choose Poisson dot dist. I need to specify three parameters. X parameter, mean value, and cumulative or not. So let's take a look at this question. What is the probability that no more than 10 craft barriers, no more than every time when you are asked by no more than, you are calculating the cumulative, right? The second question is exactly, then you need to consider cumulative should be false. Right. Let's calculate the second question first. What is the probability that exactly 10 craft barriers open every week? What should we calculate? We need to type in 10, comma. We are given the mu value 10.5. For the second question, we select false because we are calculating the probability of exactly 10. Yeah. 12.31%. No more than 10, then change false to true. Very good. Now I want to challenge you a little bit. More than 10, what is the probability? More than 10.
1 minus that.
Very good. 1 minus Poisson distribution. Right? Remember, no more cumulative probability always calculates the smaller number. No more than part, right? So if you want to calculate more than certain value, 1 minus Poisson distribution with cumulative calculation. Very good. This is how we use Poisson distribution. Okay. Another important concept, normal distribution. Do you remember last week when I talked about the shape of a data set? I showed you a symmetric bell curve. What is that called? Normal distribution. Normal distribution means you have a bell curve and it is symmetric. It's not stretched, right? That is called a normal distribution. So later I will explain why we keep talking about normal distribution, because we have a very important theorem called the central limit theorem. This is like the foundation of all important statistical concepts, right? That's why we focus on normal distribution. And normal distribution only applies to continuous data set. Continuous. Binomial Poisson distributions apply to discrete data set, countable, integers. Normal distribution is applied to continuous data set. If you want to see it, this chart shows you an example of normal distribution. So when you want to use normal distribution, you must know the mean of the data set, the expected value of the data set. Also, you want to know the standard deviation of the data set. They will be given to you. And then you will be asked, what is the probability of getting a value that is less than certain threshold? if you want to calculate mathematically, right? Notice that the area under the bell curve shows you the probability. But fortunately, we can use Excel to calculate. So once you identify a value, Excel will give you the area in green color, as you can see on this chart. So what if you want to calculate the probability of getting a value that is more than the specified value? As we just discussed in the percent distribution, 1 minus the value given by Excel. Yes. The yellow part, if you want to calculate the yellow part, you first calculate the green part first. And then 1 minus that will be the probability of getting a value that is greater than. But if you want to calculate the probability of getting a value that is less than the specified value, you just calculate the green part. And in Excel, we have another function called non.dist to calculate the green part. No matter what, the area under the bell curve represents the probability of getting the value at less than the value. So when you calculate the probability of continuous data, you always calculate cumulative probability. You always specify the cumulative parameter in the non.dist function as true. Let's see an example. Very good. I'm so happy that you guys understand this part very well. Very well. That's good. So we want to test our employee, right? We already given the information that in the previous study, the mean value is 72. Standard deviation 8. Standard deviation means most of the employees' scores changes around 72. And the standard deviation shows how many units this change is around the mean, right? So based on mean value and the standard deviation, we can draw the normal distribution curve. Now we want to randomly select a new employee's performance. What is the probability for this employee to score 60 and above? So as I said, norm.dist function will give you the probability of less than 60. So if you want to calculate more than 60, 1 minus that probability. Yes. Very good. In order to calculate the probability of scoring 60 and above, I'm going to use norm.dist. I need to specify the standard to be 60. Mean value 72. This is given. Standard deviation 8. Cumulative or not? Yes, it's cumulative. This is the probability of scoring 60 and below, right? In order to calculate the probability of scoring 60 and above, I use 1 minus norm.dist, which is 93%, right? Actually, it makes sense. Because you said in the given information, the mean value is 72, that's pretty high, right? The bar is pretty high. So the chance for your new employee to score 60 and above should be pretty high, right? It makes sense. What about the second question? What is the probability that the randomly selected manager or employee score between 68 and 84? It's a range, right? It looks complicated, but it's not. Basically, we are calculating two probabilities, right? By using non-dot-this twice. I'm going to do I'm going to use non-this twice equals to. So in the first non-dot-this, I'm going to calculate 84. Then minus 68. Does it make sense to everyone? Because I'm calculating the range above 68, but below 84, right? This is how I'm going to calculate it. 62.46%. So if you want to visualize this relationship, when I calculate non-dot-this for 84, it covers both yellow part and the green part. When I calculate non-dot-this for 68, I only calculate the yellow part. So if I want to calculate the probability of getting a score that is between 68 and 84, I use the 84 non-dot-this minus 68 non-dot-this, right? To calculate the green part. Does it make sense? Very good.